The last slide, sir.
ಬಂದಿದೆ ಸರ್, ಬಂದಿದೆ.
Okay.
Audible and visible is very fine, sir, now.
Yes, sir.
ಸೊ ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ವೆಲ್ಕಮ್ ಟು ಆಲ್ ಆಫ್ ಯು. ಸೊ ಇಂದಿನ ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ 66ನೇ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಶ್ರೀ ಅತುಲ್ ಭಟ್ ಸರ್ ಅವರನ್ನು ಈ ಒಂದು ವೇದಿಕೆಗೆ ಸ್ವಾಗತಿಸುತ್ತಿದ್ದೇನೆ. ಐ ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್.
ನಮಸ್ತೆ. ಹಲೋ everyone. Thank you.
ಸೊ ಅದೇ ರೀತಿ ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಾಜರಾಗಿರುವ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಅಧ್ಯಾಪಕರು ಹಾಗೂ ನನ್ನ ಸಹೋದ್ಯೋಗಿಗಳನ್ನು ಕೂಡ ಈ ಒಂದು ಉಪನ್ಯಾಸಕ್ಕೆ ಸ್ವಾಗತ ಮಾಡಿ ಕರೀತಾ ಇದ್ದೀನಿ. ವೆಲ್ಕಮ್ ಟು ಆಲ್ ಆಫ್ ಯು. ಸೊ ಈಗಾಗಲೇ ನಾವು ಅತುಲ್ ಭಟ್ ಸರ್ ಬಗ್ಗೆ ಕಳೆದ ತರಗತಿಗಳಲ್ಲಿ ಅವರ ಕಿರುಪರಿಚಯ ಮಾಡಿಕೊಟ್ಟಿದ್ದು, ಸಮಯಾವಕಾಶ ಬಹಳ ಕಡಿಮೆ ಇರೋದ್ರಿಂದ ಸೊ ಈ ವೇದಿಕೆಯನ್ನ ಹಂಚಿಕೊಳ್ಳಿ ಅಂತೇಳಿ ನಾನು ಅವರಿಗೆ ಬಿಟ್ಕೊಡ್ತಾ ಇದ್ದೀನಿ. ಓವರ್ ಟು ಯು ಸರ್.
Thank you, sir. Namaskar everyone. I'll speak in English for most of the presentation. So today we are here to talk about X-rays. So as you can see in the screen, the X-rays are basically invisible energy that we all have, and we all can get also. And we will discuss the physics, beautiful physics behind X-rays. X-rays is also very important to physics because when we talk about Nobel Prize, the first topic that everyone takes is X-rays. I'll discuss about that later. So getting into X-rays, when we usually talk about X-rays, what is X? If anyone asks, today's modern students or generation will basically think of this because we know Wakanda Forever, we know Wonder Woman, we know Wolverine, if you remember X-Men, or people of my class, my batch, remember Killwish from Shaktiman. They all had this hand symbol. X was what they showed. But this is not the X I'm going to talk about. What we talk about is a new kind of rays that nobody understood. So before I tell you what this X is, what these rays are, I will talk a little about the discovery of the experiments that led to the discovery of X-rays. So in 1785, there was William Morgan, who was the first person to have engaged with X-rays. We do not say he's the one who discovered X-ray because he did not know what he was doing. So when William Morgan, what he was doing was, he took a glass tube filled with vacuum, okay? Filled with vacuum means there was nothing inside the glass tube. And when he passed high, what do you say, voltage current next to this tube, he saw it glowing. He saw it glowing in the dark. And similarly, in 1886, Fernando Sanford, here he is, when he was doing some experiments related to high energy current or high voltage, there were certain photographic plates that were kept near to the wire, and they had a different kind of a marking when the current was passed. So these people were wondering what this really is. Philip Leonard in 1888 also discovered that if you pass very high current through a very high voltage, if you set up in a experiment, then it will kind of excite few metals around you to give you shock. Similarly, Nikola Tesla also later, who was very famous to have worked with AC current, alternating current, used very, very high voltages in his Tesla coil. He also noticed that photographic plates, vacuum tubes was a very important electrical component back in the day for switching. All of these components used to behave differently when you have very high voltage near it, not with it, near it. But none of these people really studied it more in detail. They just discovered this and kind of reported this to various physical societies. But in 1895, it was William Wroughton who took a tube and he realized that when you pass a very high voltage through this tube, you would see something very beautiful in the dark. What you see here is a tube, and inside this tube, I hope the mouse is visible. You see there's a metal plate here. This is connected in turn to some electrodes here. And there's another electrode over here connected to a high voltage line. And this, if you turn on in the dark, wait, this is light, no? Let's make it dark. So if you turn off everything and in the dark, if you switch on the voltage, you would see that the tube would glow. And he realized that he just placed the metal here in between. So the current would have to be, the electrons would reach here, but this is filled with vacuum. There's no wire inside over here. And the next wire you would see is over here. Yet he saw that light was generated as the electrons made their way through this path from here like this to this. And in this path, you could see a shadow kind of a structure of this metal plate over here. So this is what he observed. So this he reported to be unknown radiation. That is why we call it X. X means unknown. So he wrote a paper called The New Kind of Ray, a preliminary communication, where in this paper he mentioned, William Wrongton was the author, in 1895, that he found a radiation that is not known to us. So he named it X-rays. Back in the day, they didn't call it X-rays, they call it Röntgen rays. Okay, and this led him to win the first Nobel Prize in Physics for his discovery in the year 1900, in the year 1901. In 1901, the Nobel Prize in Physics was awarded to William Wrongton for his discovery of X-rays. And this is a painting of his acceptance speech. And you can see he's standing over here. Röntgen is standing over here. And it's a crowd filled with academicians and others, him receiving the Nobel Prize. Today, we know X-rays are much more than unknown rays. We understand the rays very well. We use these rays. Most of us use these rays. We have come across these rays when we talk about injuries, bone injuries, fractures, and all this. But back in the day, when it was first discovered, it was not just used for detecting bones and fractures. It was used for almost everything. You see here, a doctor is performing a surgery by making a patient sleep on an X-ray emitting, X-ray emitting device. And those X-rays are passing through, because the beautiful property of these X-rays was they could pass through human skin. So these X-rays would pass through this table here and reach the doctor's eyes. And there's a film here, photographic film here. So on this film, when the film would glow, the doctor would know, oh, here there's the bone, here there's no bone, and things like that. And here you see a chest scan of a person to see if the rib cage is all right and all these things. So X-rays was used as a common entity in medical science, not like it is used today. In fact, today we know X-rays for identifying bones and tissues. And you can see here beautifully how the bone structure, the rib cage is visible when an X-ray is passed through it, and the bones do not allow the X-ray to pass through, and the skin does. So X-ray on a white sheet or a blue sheet, like I've made the slide designs today. On this blue sheet, the X-ray would touch and it would make the region black. So wherever the bones absorb the X-ray, it would not reach this sheet and it would still be white. Tissues would be semi-transparent and bones would be very hard. In fact, if you have metal, like some of us, when we have fractures, they say a rod is fitted into the bone. So in such a case, you can see the rods like this in the next. Okay, today we also know for tooth checking. This is actually my own X-ray. A tooth X-ray is taken like this, where you see the entire jaw, all 32 teeth can be seen. Especially if you want to see if a wisdom tooth is coming out, this is what they make you do. But one of the first uses of X-rays was to measure your foot size. Chappal angadiyalli, if you were buying a footwear like a chappal or a slipper or sandals, they would take an X-ray of your leg in this device. You can see here, this is the device on the right side. On the left side, you see that the person is standing with the leg inside, and then one person is observing from the top. And the person, the footwear owner, shop owner, is looking from this window here. There are multiple windows. So with this, they could measure the size of the foot, if the shoes is fitting or not. And with that, they could sell the shoes. But then people realize that X-rays are not really safe. And why so? We will find out. So first, let's understand what are X-rays. They are basically electromagnetic radiations. And if you measure the wavelength of this electromagnetic radiation, because you know electromagnetic radiation is nothing but a wave, and every wave has crest and troughs. So the distance between one crest to another crest, if you measure, for an X-ray, you would find this distance to be about 0.05 into 10 power minus 9. So if you take 1 meter scale, and you divide it by 100 crore divisions, or if you take a, let's say 1 centimeter, if you take 1 centimeter and then you divide that by 1 crore divisions, 1 centimeter you divide it by 1 crore equal divisions, then that one division is equal to 1 nanometer. So here That is the wavelength of an X-ray. Okay, this is what I've written. And white light, usually the light you see, which is not X-ray, is usually 600 nanometers, 600 times large. Okay, or 1200. If you take the smallest wavelength of X-rays, light is 1200 times larger than light waves. Okay, X-rays are that big, that small. Okay, so if you talk about the electromagnetic radiation, the smallest wavelength, you see visible light, the color that you see, all the colors that you see here is this kind of a wavelength, 10 power minus 6 to 10 power minus 9. From there, if you go smaller and smaller and smaller and smaller and smaller, this is the region where you have X-rays. So X-rays have very high frequency and very, very, very small wavelengths. And this has led us to study various aspects of medical physics. X-ray helps us in understanding X-ray crystallography, mammography, CT scans, or even in airport security, we use various kinds of X-rays. I'll talk about that later on. So first, let's understand how to create X-rays. Now, rather than me talking simply and you listening, let's do an experiment. Okay. I believe all of you are students of PU, if not at least high school. So you know what an experiment is. When you do an experiment in school, you have aim of an experiment, apparatus, and so on and so forth. So let me do the same way here. How to create X-rays. So idea is simple. Let's do it the way Wrongton did it. But if you look at how Wrongton did it, you see his lab over here. It looks very dangerous, very scary, right? In fact, you can visit this lab today here in Denmark, and most of it is kept the way it is. And these are the various tubes that Wrongton generated the X-rays from. Okay, but let's come back to doing an experiment. Okay. Oh yeah. Before you do an experiment, you need the apparatus, and that is called sorry, it's not cold tube, it's the Coolidge tube, because it was modified by Coolidge to be like this. A modern Coolidge tube is something like this. And this modification is what helps us generate X-rays very easily today. Okay. So producing X-rays, if you want to produce X-rays, then these are the ways. So let's look at the experiment. Aim of the experiment is to produce X-rays. Apparatus required is a source of electrons. Of course, we need electrons. Like I told you, Röntgen passed very high current, so electrons were the sources. And you need this electron to collide with something, so you need a target. And then high voltage, because the electrons have to be accelerated. And of course, the Coolidge tube is required. Okay, be careful if you're trying to do this. You can't do this at home because high voltage is very dangerous. You don't want to get electrocuted. Okay, and then it would lead to some kind of disaster. So producing X-rays, I told you Coolidge tube, we have a cathode and an anode here. Okay, to this we'll connect high voltage source such that when you do this, the cathode will emit very high fast moving electrons, and they are emitted from this metal over here. They will go fast and hit this metal piece and collide with this metal piece. And we have kind of created an angle at this metal piece here so that the light is actually coming on this side. Okay. So the circuit required, like I told you, the cathode and anode need to be connected to a high voltage source. Okay. The cathode, for it to operate itself, you need a low voltage. Okay. So this is basically usually a tungsten filament or any other filament that will give out electrons. And that will work if you connect it to a low voltage source. So when you give a voltage here, it will emit electrons. But for these electrons to move fast from the cathode to the anode, we will connect that in turn to a high voltage source. And then at the anode, when the electron strikes, we should have X-rays. Okay. So the theory of an X-ray is simple. If you give some energy, an electron moves very fast, like this child here. If the parent is holding, then the child will not move so freely. But if the child is given the freedom to move in the mall, it will start running around. Electrons also need energy. So if you give them the freedom, they will move very fast. And then you need to stop them suddenly. And when you stop them, energy will be released as X-rays, which are electromagnetic radiation. So let's see. The filament is heated with a high voltage source, like I mentioned, and then you connect it to like 30 to 100 kilovolts, 100,000 volts. And when that high voltage is given, the target is connected, and then basically the electrons get fired. And of course, this is going to create a lot of heat. So you need cooling, and you have to be very careful not to electrocute yourself. So if you are doing this, then this is how it works. The filament will basically emit some electrons, which are usually passing through the coil. But when you pass high voltage, they'll move from here, hit this tube here, and generate X-rays. This is the working. And the result of this experiment would be you will have produced X-rays. But what are your observations? The direction of production can be controlled by the angle of the target. You can see here, the target angle here, if you change this direction, if you make this flat, then the electrons move backwards. If you make it more angle, more slant, then the electrons will move this way. Sorry. The X-rays will move this way. So X-ray direction can be controlled by the angle of the anode, right? And the intensity would be controlled by the low voltage source. So that filament that is connected to the low voltage source, if you increase that voltage slowly, then the intensity of the X-ray would increase. And the energy of the X-ray, by which energy it comes out. Now, intensity is how much X-ray comes out. Energy means for the little amount of X-ray that is coming out, what is the energy, right? So intensity is the collective energy, and individual energy is increased by high voltage. So the energy of the X-ray could be controlled by high voltage source. Okay, and this is not really helpful. So we can study this. Okay, so when you talk about X-ray spectra, because what kind of X-rays are generated, if you find out, if you calculate the wavelength of the X-ray generated, various wavelength of X-rays may be created. Whatever is the nanometer scale, whatever is the wavelength of the X-ray, if we plot all of them, for this lambda, how much do I find? For this lambda, how much do I find? For this lambda, how much do I find? I will get these various points and I'll get a graph. What you'll see here is the X-ray spectra, which is basically how the X-rays are generated. The intensity increases with wavelength. Okay, there's a minimum wavelength beyond which there's no generation. Okay, because that is the amount of energy required for the electrons to be liberated from the metal. I'll come to that later. And from there, as you increase the wavelength, the intensity of the X-rays increases. Sometimes it goes very high, comes down, and it reaches one point, and then the intensity decreases continuously. This continuous plot, a straight line that you see here, is called the continuous spectrum or the Bremsstrahl arc. And these sharp cones that you see or rises that you see in this graph are called the characteristic X-rays. Okay, what are these and how to create, we will discuss. So continuous X-rays where the wavelength is continuous, the intensity is maximum at a particular wavelength. Okay, the intensity is maximum at one point here, and then it will stop, it will decrease. And intensity minimum depends upon the voltage. Whatever voltage you apply, beyond certain voltage, only the electrons will be generated, otherwise they will not. Okay, so we will realize lambda maximum is directly proportional to V. I can skip these calculations because I have a lot to show, and calculations can be found in any book that you can find. Right, so you'll find that lambda minimum is inversely proportional to this V. So if you do the calculation, because lambda V is equal to C, which is the speed of light, you'll get lambda minimum is inversely proportional to the V maximum, voltage maximum of the, velocity maximum of the electrons. So you'll see that this is the relation, and you'll realize that the maximum velocity can be obtained by increasing the voltage because they are directly proportional. Okay. And this further calculation, when you apply Planck's law, you get E is equal to h nu. So maximum frequency is equal to EV, which is called the Dewey-Hunts, which basically means that if you increase the voltage, the frequency will increase, right? If you increase the voltage, frequency will increase because E is a constant. It is charge of an electron, and h is a constant. It is a Planck's constant. Now coming to continuous spectrum, how does it generate? So let's take this example. When an electron passes through a material, like I told you, from the cathode, it hits the anode. So let's say this is the atom of the anode. Okay, whatever material is the anode made up of, this is the material. And one electron is short and it comes here, passing through here. And when it comes here, the nucleus usually attracts the electron. When the nucleus attracts the electron bends or it slows down. Usually electron moves with some energy. So in this example, I've given you 90 kilo electron volt. You can convert this to joules. 1 electron volt is 1, if you want, you can write this down. 1 electron volt is 1.6 into 10 power minus 19 joules. So 90,000 electron volt means how much joules? You can calculate. Okay. So when a 90 kilo electron volt, 90,000 electron volt electron moves inside the atom like this, the nucleus slows down the electron So the electron loses some energy, and that energy comes in the form of photon or electromagnetic radiation. In this image, you see that the electron is 90 kilo electron volt, and as it loses energy, it loses 80 electron volt as energy, and the remaining 10 kilo electron volt will be with the particle. It will move slowly like this. Look at another example. Okay, 90 kilo electron volts breaks up into a photon of energy 60 kilo electron volts. The remaining 30 is the energy of the electron. You see, in the earlier case, it was 90 is equal to 80 plus 10. Now 90 is equal to 60 plus 30. In the next example, this 90 can break into 85 electron volts photon and 5 electron volt electron. So you can see this 90 can be broken into any form. So thousands and billions of electron, when they're undergoing this, different electrons, depending upon how they come to the nucleus, how close they come to the nucleus, their loss of energy can be of any value. So 90 can be 85 plus 5, 80 plus 10, 40 40, sorry, 45 plus 45, 40 plus 50, 1 plus 89, so many things. That is why you have continuous value of voltage, wavelength. Okay, see this in zoom now. The electron comes around. As it turns near the nucleus, this is what happens. As the nucleus bends the electron, you see it loses some energy. This leads to the continuous X-ray spectrum. This image is not required. This is the image we want. So the number of photons for a given wavelength is constant. Some value increases and decreases, but for all wavelengths we will obtain. Okay, the value of the energy of the photon in the first example I showed you, it was 80, 10, 30, 60, 85, 5. So 80, 30, 85. So these are the values, and everything is possible. 80, 81, 82, 83, 84. Any value is possible. That is why we call it a continuous spectrum. But of course, there's a minimum value. You can't find a photon less than 10 electron volt or something like that. But beyond a certain value, all values, depending on the intensity, they may vary, but all values, at least one photon is emitted. And that is called a continuous spectrum. Okay. So how is that possible? Of course, photoelectric effect, we learned that in the photoelectric effect, the kinetic energy of the electron is given by the energy of the photon it absorbs minus the energy it loses to gain freedom. That is the binding energy. So if you just mix this, we call it the reverse photoelectric effect. The energy of the photon comes from the kinetic energy of the electron with which the electron enters the nucleus minus whatever is the binding energy required for the electron to go join the nucleus. Okay, because it slows down, binding energy is kind of pulling on it. So that much energy is lost, and the remaining energy is the energy of the photon. So that is how it works. Okay, of course, this is Dewey-Hunt's law again. This comes from Einstein's photoelectric effect. And this is how continuous X-rays, the X-rays with all possible wavelengths are obtained. Then there are those peaks that I mentioned. These small carrot-like peaks that you see, small spikes that you see in the graph. These are nothing but characteristic spectra. Characteristic because they are fixed. These peaks come for a specific wavelength, either here or here or here or whatever. So there is a characteristic to them. And that is what we are going to find out. Multiple of these peaks are usually given names like K alpha, K beta, and I'll explain that what that means. Now, how is a characteristic X-ray produced? Let's see. A characteristic X-ray is produced when an electron comes inside the atom and knocks down another electron. Okay, an electron comes inside the nucleus and knocks down another electron, and when that happens, there is a vacancy generated. When a vacancy is generated in the inner orbit inside an atom, the atom does not like it. So then electron from the higher orbital jumps inside. And that energy is, whatever energy is there in the higher orbit is lost to come to the lower orbit. And that loss of energy is given out as a photon. And of course, to fill in all the vacancies, all the higher orbital electrons will simply jump inside one by one. And in this process, many photons are generated or lost. Okay. So characteristic X-ray formation is because of this. And cathode electron, okay, I'm sorry, this is black. I hope you can still see this. The cathode electron over here, which comes from the cathode, comes from the high voltage. This is high voltage is accelerating this, so it comes here and hits this one spot over here. When this one spot is hit, the electron here is lost and the cathode electron also is lost. Both of them leave the atom. There's nothing there. So you have a vacancy. Now, if this vacancy is filled in by this electron here, then we have some amount of energy. Okay. But if this vacancy is filled by this electron over here, then there is another difference. So mark the shells here. I'm not sure if this electron, the inside electron, this electron is 2 kilo electron volt. This side it's 12. And let's say the inner one here, or this vacancy is 69. Just numbers. Okay. Forget kilo electron volt. You just remember the values. So if an electron is here, it has energy 1. If it is here, it has energy 2. If it is here, it has energy 12. And if it is here, it has energy 69. So now when an electron jumps from this point to this point, okay, when an electron jumps from that point to that point, the energy that the electron would give up is about 57 electron volts. Whereas if it is jumping from a higher orbital, like I've shown there, then the electron loses less energy. So, I mean, more energy. Okay. So each single time, the electrons lose energy as they jump from one orbital to another. And that is how characteristic X-rays are produced. Now, because these energies are fixed, the peak of the X-rays are at a fixed wavelength. Okay. So when you saw the graph, there was a peak for one particular wavelength and there was another peak for another particular wavelength. That happens because when an electron is there in one shell and it jumps to another shell, the energy given out is the difference of those shells, which are fixed. For a given atom, those shell differences are fixed. And that is why the characteristic X-rays are fixed for certain values. If an electron jumps from L shell to K shell, we call it K alpha. If an electron jumps from M shell to K shell, we call it K beta. N shell to K shell, K gamma. So anything to K shell, we call it a K electron or K photon. From L shell, L to K, direct jump, alpha. Second level jump, M to K, it's beta. N to K, it's gamma. So these are the terminologies we usually use. Okay. So an electron from L shell to K shell, it is K alpha. M shell to K shell, it is K beta. N shell to K shell, it is K gamma. Similarly, if an electron is jumping from M shell to L shell, okay, it is right next to each other. L and M are right next to each other, so you call it L alpha. N shell to L shell, it is L beta. O shell to L shell, it is L gamma. So these are the kind of names we have. Then this is the picture diagram we have. Okay. So K, L, M, N, these are the names. So from K to L to K, K alpha, M to K, K beta, N to K, K gamma, O to K, K delta. Similarly for L alpha, L beta, L gamma, you can have this for multiple values. Okay, so characteristic means the peak values let us know the characteristic of the material. That is why we call it the characteristic X-rays. If you understand where these peaks are, you will understand the material that is used. Okay, so yeah, this is what a typical X-ray graph looks like. You see that the peaks are obtained for specific wavelengths for a given material. So here, this for a particular material, you see that one K alpha is for this particular wavelength. I can mark it if you want. Let's see. Yeah, K alpha is particularly for this line. K beta is particularly for this. K gamma is particularly for this. L alpha for this material is here. L beta is here. M alpha is here, and so on and so on. So these lines are fixed for a given material. This is what is helpful. Okay. So all in all, what we've studied two types of X-ray radiation. That is continuous X-rays, which is also called the bremsstrahlung, where an electron is not really doing anything. It is simply losing energy as it passes through the nucleus. It is not interacting with anything else. So as it passes through the nucleus slows it down, and that difference in energy, the slowing down energy, is given as photon. Whereas the characteristic X-ray is because the electron hits another electron, and now you have ejected electron and redirected electron. The initial electron hits one electron. So the initial electron goes in one direction. The electron it hit goes in one direction. So there's a vacancy here. And that vacancy, when it is filled by another electron in the atom itself, it gives out energy, which is a fixed wavelength, fixed frequency, and that is called characteristic X-rays. Now, characteristic X-rays are called fingerprints of various elements. Okay. Today, we are all very well aware that we need fingerprints to open our phone. How is it so secure? Once upon a time, there was password. And if I tell my password, if someone sees my password, they could also open my phone. But today, my phone opens only because of a fingerprint. And my fingerprint is my fingerprint. No one else's fingerprint can open it. So when the fingerprint is scanned, the phone knows this is me. Whereas in case of password, the phone would not know who entered the password. It would just think that the password is right and it would open. But in case of fingerprint, nobody else can have that fingerprint. It is unique to me. Same way, characteristic X-rays, those peak values I showed you, those lines I showed you, those are unique to different elements. And that is why they are like the fingerprints of various atoms. Okay. So each atom has a fixed KL difference. We call these the forbidden gap and all that. So these shell differences are fixed for every single atom. And identifying where the K alpha, K beta, K gamma is, we can find which element you're using. Therefore, it's like the fingerprint. So this is the meaning of it. So if you use some value of wavelength, let's say 25 kilovolt, the green line, for a given material, the intensity will be low, but the peak will be at this value itself. Oh, value is already given. So yeah. So at 1 Armstrong, you have a peak K alpha, and then the second peak L alpha is at 1.5 Armstrong. So these are fixed. So this means that the material is some material. Okay, let's say iron. So for iron, I'm getting this. If you increase the voltage to 50 kilovolt, if you increase the cathode and anode difference to 50 kilovolts, then you'll see that the intensity increases, and then the peaks are again at 1 Armstrong and at 1.5 Armstrong. So the peaks are exactly at the same point. So for any given material, if you change the voltage, its intensity may increase, but these peaks are fixed at those points. That is why it's going to be the fingerprint. And this is how we find it. For any given material, okay, these are the peaks we have. So if you have chlorine, you'll have a peak here at 2. Let's say 7 kilo electron volt, whereas oxygen would have it at 0.5 kilo electron. Iron, which I mentioned right now, is at 7 kilo electron volt. So identifying these peaks, where the peaks exactly occur at which value of energy or wavelength, we can identify which material or which element is being used. Now, how do you do this? How do you do this experiment, and how do you find which element, and how did the element come into picture? We basically use diffraction. Normally, when we use diffraction, we use light. Second PUC students know what diffraction is. Bending of light around obstacles is called diffraction. So usually what happens is, if you have a grating, okay, a grating is basically something like a glass plate or a metal plate with some kind of obstructions. Like here you see there are ditches formed and light is passing through this. Okay, same way here you see this. There are these kind of speed breaker kind of structures here on this material, and light will simply pass through it. And because these value, this D value that I've written here, these difference between these two peaks are same as the wavelength of the light, almost the same, then the light will bend. This is diffraction. On a reflection grating, you'll see for the same structure, for the same D value, same peak, all that, but this material does not allow light to pass through it. But if it reflects light for the same obstacle size, the light is diffracted. So diffraction means bending of light, or kind of deviation of light when it comes across an obstacle where the obstacle size is very close to the wavelength of the light used. This is diffraction. Okay. Typically for white light or visible light, we use a grating which has about 600 lines per inch, which roughly means you need to use a wavelength of 200 nanometers. 200 nanometers is less, very less wavelength compared to violet. So this is not visible light, but it is still not 1 Armstrong. This is still not 0.1 nanometer. So these are not for X-rays. So how do you have a diffraction for X-rays? So the grating for an X-ray, if you want, then the wavelength of an X-ray you will use is 10 Armstrong. So 10 power minus 10 meter. And the smallest grating lines that we can generate right now is about 10,000 Armstrongs. So what we do is we use a material such that the space between the atom itself can be like the grating, right? Because within any material, the space between two atoms is usually 1 Armstrong, which is nothing but the wavelength of light, X-ray. So it can be used for diffraction as diffraction grating. So then what we can do is we can use a material, shine some X-ray on it, and the difference between the atoms of that material will lead to diffraction. So this is what happens. When light is shot into the material, it absorbs that X-ray, because of course X-ray means energy and energy is absorbed by the electrons. They will get excited for a while, but electrons don't like excitation, so they will emit these values and the system is normal. So what really happens? A light wave X-ray is incident on the material. The electrons in that atom kind of excite. They get excited, they vibrate a lot, and then they lose that energy in the form of the same photon, because electron has come back to it. The atom is same before and the atom is same after, then the amount of light absorbed should be equal to the amount of light given out. Shine light through it can become diffraction gratings for X-rays only. So you see, when the atoms form the structure where the distance between the atoms is same as the wavelength, then as you bend the beam, okay, as you incline it on an angle, it will reflect back the same beam with an angle, just like a reflection. And this is called diffraction. So now if you increase the angle of diffraction, you will see that the diffracted beam will also change the angle, and then there is some kind of a difference. You see the waves don't meet properly. Sometimes they do, sometimes they do not, depending upon the bending. In this case, you see the waves are meeting, and in this case, you have constructive interference, okay, or we see a peak of X-ray coming out, okay, and sometimes it does not meet, okay, because of the angle it does not meet, and there the peak will not be formed. So all of this can be measured using something called as a Bragg spectrometer. I'll not go very much into detail, but what you have here is you have a sample kept here, a material that you want. You will keep that material here, and then you'll shoot it with X-rays, high energy X-rays. The X-rays have to be very fine, so we'll use some collimators or whatever. And when the X-rays shoot the element at various angles, like I showed you here, you see here, as the angle changes, the beam coming out also changes in angle, right? So the sample's incident angle is something, the reflected angle is something. These two are different values. Okay. So what really happens in this machine, you can rotate this sample here on a table. It's a turntable, and you can rotate this entire arm. It can be rotated such that you rotate this angle, and then the beam of X-rays will be at along certain direction only. So you measure it here, nothing here, nothing here, nothing here, nothing here. You'll have a peak. Here, nothing here, nothing here, nothing here, nothing here. You rotate this by a slightly more angle, then here you'll find nothing, here you'll find a peak, but here nothing, here nothing, here nothing, and so on. So for different angle of the specimen, different angle of the observation, you will realize there are various peaks that is found on the X-rays that is coming out. And these peaks can be marked. This is called X-ray spectrograph, okay, or spectroscopy. When the X-rays are studied, these peaks come out at specific values of these angles, glancing angles, which means they come out for specific values of lambda. And understanding that value or peak, we can understand crystal lattices. Because you see different types of crystals. For example, iron, chromium have this kind of a structure here, where you have six, I think, right? No, eight atoms forming this box and one atom in the center. This is how iron forms the bond. Whereas if you take aluminium, nickel, gold, silver, or copper, these are all shiny metals. These metals, if you see, then it's not simply eight atoms forming the structure. You'll see there's eight atoms plus one in the center and one on every side. So 1, 2, 3, 4, 5 plus 8, right? 13 atoms in one unit cell. And these repeat again and again and again and again. It will repeat. Whereas if you take zinc or magnesium or cadmium, they have this hexagonal kind of a structure. So in each of these cases, what you see is the space between the atoms, they are different. Here, the atoms are quite far apart. Whereas here, you see the atoms are very close, very, very, very close. Here, the atoms are quite close, but very far. These two atoms are very far. These two atoms are very close. So shining an X-ray at different angles on the same material and seeing what kind of peaks it produces, in which angle you'll get the maximum light back. That will give you the characteristic X-ray peaks. And when that happens, you can find the fingerprint of that material that is used to study this. Here's a device. Okay. Here's a device that actually is what I explained. You have the source here. X-ray source is here. It's quite dangerous, so it's inside. And the X-rays travel through this tube and reaches the sample here. The sample is usually kept here. And once this, what happens is this angle will change for the sample. So the sample will be like this, it may become like this, whatever. And once the beam hits the sample, X-rays may come out in one or two directions. Maybe here, not here, maybe here and not here. So this arm here will rotate. It will go like this. And at certain angles, from this angle maybe, this angle no, but this angle maybe. So at certain angles, it will detect the X-rays coming out, and that will tell us, give us the fingerprint of the material. So here is the working. I'll just switch on the video. Let's see how it goes. So you see, the person is rotating the angle of the specimen and the angle of the arm using the various settings available. And when the beam is short, you see this part here is glowing, so the X-rays are being generated. We'll come hit the crystal and see if there's a peak over this at this angle or not. Okay. Similarly, I have another video of the same instrument. In this instrument, you see it's set into automatic mode. So as it moves along, you'll see this peak observed at certain angles. Right. I hope you saw that. Let me play it again for you. You see now when this arm moves like this at a particular angle, you'll see in the graph the peak goes up. The number of photons received is very high. Okay, let's see this. So as the arm rotates, you'll see here is there's a peak, here there's a peak, here there's a peak, and it reduces. So as the angle of the hand changes, you will find the different peaks. Once you find these characteristic peaks, you will be able to find what material you're studying. And here you'll see there's a continuous X-ray spectra. There's a continuous X-ray spectra. X-rays of all these values are identified. Nothing great about it, but at this value and at this value, maximum number of X-rays are identified. So this is how we have X-rays, and this is how we usually study X-rays to find various materials. Like the K alpha lines of various materials are plotted over here for the energy level. If you do an experiment and you find out that a certain wavelength, which means you realize wavelength and energy are quite related. So this wavelength in this energy, this wavelength in this energy for certain photons. So if you take a material and you find that the wavelength is producing the maximum at 6.5 kilo electron volts. So if the maximum photons you observe for the X-ray is at 6.5 kilo electron volt, then you can be sure that the material has iron, K alpha of iron. Okay. And of course, it'll have a peak here as well and here as well. But sometimes these peaks are unique. The space between these peaks are unique. For another material, slightly variation in the material. For example, nitrogen and oxygens. We read it table number 7 and 8. If you change by just one proton, then the gap between these spikes are different. Sometimes it'll be one will be here, one will be here, one will be here, one will be here. So identifying the distance between those lines, you should be able to identify what material is being used, and that is how it is used to identify the materials. But all of this is in the lab. In the real world, when you look at X-rays, this is how it looks like. X-rays are usually passed through materials, and if the X-rays are absorbed by the material, we see the X-rays do not pass through, and then we can kind of estimate what is inside. For example, the first three X-rays here for the shoe, this is an astronaut's shoe. When you pass it through an X-ray, you'll realize there are no metals, only these points are metals. That's why they absorb the X-rays, whereas the softer materials do not. The cloth materials do not do not absorb the X-ray, and they allow the X-rays. A stingray, you see the body here, the various bones, you see how beautifully the bones are spread out, just not like humans. So this can also be, or flowers. You see the center of the flowers, they absorb because they are thick and they absorb the X-rays. Whereas the outer petals, they are not completely invisible, but they still allow light to pass through them. They're semi-transparent. So you see kind of a faint light over here. Whereas very important use of X-rays here. You see, this is one painting, okay, a medieval knight painting. And what you realize is when you take an X-ray, you'll find a ghost image. Now this head over here This head over here basically represents the same head. It's the same height. But you'll realize much before this painting was painted, it was also painted before for pretty much the same person, but younger because the head was at this level. This was the height level. So the painting was done first. You see one leg over here, the new leg over here. So this is an old leg. The new leg is like this, so it's like this. Old leg is like this, and so on and so forth. What this really helps us identify is because these various paints are made up of various materials like metals and all these, we can identify if a painting is fake or real and so on. This painting here has been redone, redesigned, and painted over, and therefore it is original, done by the artist. Because if someone is trying to copy this painting, then they would have directly painted it onto a canvas. And of course, very important use of X-ray today is when you go to airports, when you go to railway stations, these X-rays are used to keep you safe. Why? Because they are used in the TSA, the Terrorist Striking Agency, or whatever it is in the US. In India, it is CISF, the Central Industry Security Force, which is the police like guards that stand in the airport. They let you pass through, they do a security check, and in that time, they put your bag onto a tray and it goes into a machine and comes out. Sometimes, if you're not carrying anything dangerous, your bag will pass through, nothing will happen. But sometimes they'll say, call a person and say, there is something in the bag, show it, show it. So, all of that is because of X-rays. When a bag, when certain valence of X-rays are passed through the bags, it passes through the materials, different materials. So here you see the first image, there's shoes, there's bottle, there's a headphone, there's a kind of a deodorant, there's a specs, goggles, earphones, camera, and all these things. All these things allow light to pass through, the X-ray to pass through them. So you see none of them is quite dangerous. Whereas here in the lower bag, you see in this green bag, there's a very hard metal gun-shaped item. It's metal, it's probably a gun, and that is how they catch the terrorists. Whereas sometimes what happens, it's quite tricky because you see some materials of the guns are not all metals. Certain pistols have plastic handles or plywood handles or just wooden handles. They are not metal. So in that case, it would look like this. You have metal wrenches, metal spanners, and all these. The zip of the bag, all these are metal, so they are dark. But the gun has a metal which allows certain wavelength to pass, so it's not completely dark, but dark blue. But the handle, where is the handle? Handle you've drawn here, but it's not very thick. It is semi-transparent, which means the handle is not made up of metal. You also have a bottle filled with some kind of liquid. That's why it's orange and also and many things like this. So X-rays are something that is fascinating and very unique. X-rays, we didn't know what they were initially, and when they were discovered, we knew that there is something called electromagnetic radiation, and we find that X-rays have the same properties as electromagnetic radiation. So we call them X-rays today still because that's the name given, but we know what they are. We don't give them any other name. And because Röntgen was the one who discovered it, we sometimes call it Röntgen rays. But these X-rays are very, very, very powerful. In fact, I told you initially that X-rays were used in every medical operation for selecting footwear and chappals and sandals. But later they realized these energies are so high that they can cause cancer. And that is why today X-rays are only used to identify very important things like I told you in the airport to identify terrorists, to identify weapons, or in the medical field only when a bone is broken or you need a root canal. That's how they identify where the bones are. But even then, sometimes you see the doctors hide behind the X-ray machine or say, be careful and all these and things because X-rays are so powerful that if it lands on your hands and your hands kind of develop mutation, then that will lead to cancer. So with this, I would like to end my talk. If any one of you wants to study more about X-rays, these are the books I've used to refer to create these talks. You can find them online. You can find them. You can buy these books because I suggest Concepts of Physics by H.C. Verma is like the holy Bible of physics, and you have to have it. Every Indian must have this. Apart from that, Engineering Physics is a beautiful book that talks about the history of X-rays and all these. And Solid State Physics by S.O. Pillai is also a great book that can be used to study X-rays. If anyone of you have any doubts regarding X-rays, my email ID is right here, so you can use it to ask me questions and all these things. Thank you.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ವಿದ್ಯಾರ್ಥಿಗಳು ಯಾವ್ದಾದ್ರು ಕ್ವಶನ್ಸ್ಗಳಿದ್ರೆ ಇವತ್ತಿನ ಎಕ್ಸಸೈಸ್ ಟಾಪಿಕ್ ಮೇಲೆ ಮತ್ತೆ ಡೌಟ್ಸ್ ಇದ್ರೆ ಈಗ ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ ಫ್ರೀ ಆಗಿದ್ದಾರೆ, ಕೇಳ್ಬೋದು. ಅಲ್ಲ ಸರ್?
ಸರ್.
ಯಾವುದೇ
Yes, sir.
ಕ್ವಶನ್ಸ್ ಹಾಕಿರ ಸರ್ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ. ಸೊ ಕಳಿಸಿದ್ರೆ ನಾನು ನಿಮ್ಗೆ ಚಾಟ್ ಇಮೇಲ್ ಮುಖಾಂತರ
Yes, sir.
ನನ್ನ
Sure.
ಕಳಿಸ್ಕೊಡ್ತೀನಿ ಸರ್.
Sure. Sure.
ಸೊ ಎನಿವೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್. Deliver a talk, very informative and insightful talk on X-rays behind the physics. ಮಕ್ಕಳಿಗೆ ಭಾರಿ ಸರಳವಾಗಿ ಹಲವಾರು ಉದಾಹರಣೆಗಳ ಮೂಲಕ ಎಕ್ಸ್ರೇ ಯಾವ ರೀತಿ ಪರಿಣಾಮ ಬೀರುತ್ತೆ, ಯಾವ ರೀತಿ ಕ್ರಿಯೇಟ್ ಆಗುತ್ತೆ ಅನ್ನೋದನ್ನ ಭಾರಿ ಸರಳವಾಗಿ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡರಲ್ಲೂ ಕೂಡ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ. ಸೊ ಬಿಹಾಫ್ ಆಫ್ KSTA ಅಂಡ್ ಮೈಸೆಲ್ಫ್, ಥ್ಯಾಂಕ್ ಯು ಸರ್.
Okay, sir. Thank you so much.
ಹಾಗೂ ಇಂದು ಹಾಜರಾಗಿದ್ದ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳು, ಸಹಪಾಠಿಗಳು ಮತ್ತು ಅಧ್ಯಾಪಕರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಮತ್ತೆ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೊಂದು ಸೂಚನೆ, ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಚೈತ್ರಾರವರು ಅಮೈನ್ಸ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಅವುಗಳು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಬೇಕೆಂದು ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು.
Thank you, sir.